Hey everybody, Dr. Phil here. So this video is going to be about just some basic statistics and some of the tools that can be required in business analytics. So let's just talk about some basic statistics first. So first thing, population versus sample. So think of the population as a group with something in common, but obviously it's too many people, it's too expensive, too time consuming to, get the data from every single person, individual, whatever, what item, whatever it may be. So the parameter is a characteristic of a population. So example would be like a survey of all restaurants in the country. So what we do is we get a sample, right? I'm sure you've heard that term, sample. This is a subset of a population, and we got to make sure that the sample is representative of the population, right? And here, this is where we use the term statistics because that actually means the characteristics of a sample. We use these to make inferences, basically educated guesses, conclusions about the characteristics of a population. So an example could be a survey of selected restaurants. A couple of different types of statistics, descriptive statistics that measures either describe a population or sample. So things like the mean, the median, the mode, bimodal, multimodal, so on and so forth. And then inferential statistics, think about the idea of like the word infer, right? To kind of, I infer that in kind of making an educated guess. So measures calculated only using a sample, and that's where the inference comes in because you didn't test the whole population, right? You just tested the sample. A hypothesis is a proposed explanation made on the basis of limited evidence as a starting point for further investigation, and this is where inferential statistics kind of is used. So sampling methods, there's a lot of different types. This list here is not exhaustive, but simple random sampling, stratified random sampling. So, think about groups or strata. Cluster sampling, we might, identify people or individuals by attributes, or items by attributes and try to cluster them together just to make the data analysis a little easier to do. Or convenience non-probability sampling. With regard to probability distributions, a random variable quantifies the outcomes of random occurrences. Data distribution shows all possible values for a variable and how often they could occur. And then the probability distribution is a statistical function that describes the possible values in a population and the likelihood that any given observation, i.e. the random variable, can take a given range or value. So here we see an example of a probability distribution. So in this case, it's process time, number of orders, and then you can kind of see, as you go from left to right, kind of where, how that probability distribution falls, with respect to the number of days, like 2-7, it's obviously 7-12 is very popular, 17-22 is not, so on and so forth. Types of numerical data, continuous versus discrete. So continuous data can be any numerical value, not just whole numbers. So really there's an infinite set of values between any two observations, right? Just like how far down into the weeds do you want to get, right? How much do you want to zoom in, if you will? So examples could be height, weight, and currency. Discrete data, these are like whole numbers, like so integers only. We have a finite set of values between any two observations. Examples could be inventory, vehicles, manufacturing, or more manufacturing plants. With respect to measures of central tendency, these are used to describe the center point of a data set. And these are probably, the first three are probably, you may have not heard of the bottom two, but the first three, obviously the mean is the average, right? The median is just the middle number, as they say, the midpoint of the data distribution, as they describe it. The mode is the most common observation in a data set. The kurtosis is the distribution shape, i.e. the data, is the data central, or is it, does it look kind of like that? Or is it more like kind of like flattened out like that? And then symmetry just speaks to, obviously if it's perfectly symmetrical, then it's a perfect perfect distribution. Obviously that's pretty rare. Very unlikely that's going to happen. There's usually some what we call skewness in the data somewhere, like skew to the left or skew to the right. So speaking of skewness, we see here some examples of right skewed, right, and left skewed distributions. Now, measures of dispersion describe how dispersed, the data set is. So the range is simply the highest number, the maximum, subtract the minimum number. The interquartile range is the four quartiles. The variance is the average of the squared deviations from the mean. And then with respect to the standard deviation, it's simply the square root of the variance. And of course, same unit it would be expressed in the same unit as the data values. For continuous probability distributions, this of course is the normal distribution. What you're seeing here is what we call the empirical rule, the 68, 95, 99.7 rule. Basically, 68% of the data observations will fall, as you can see, plus or minus one standard deviation from the mean. 95% of observations will fall plus or minus two standard deviations from the mean, and then plus or minus three distributions will fall just shy of 99.7% of data. So the standard normal distribution, the special case of the normal distribution. So this is, of course, it's theoretical and it's used for comparisons, and it's used to calculate the probabilities of individual observations. So where the mean, the median, and the mode would all be zero, and the standard deviation would be one because it's perfectly symmetrical. Again, very rare that happens. The z-score, the number of standard deviations a data point is from the mean. So z is basically x minus the mean divided by the standard deviation. Now, the confidence interval, we'll talk about the point estimate versus the confidence interval. So the point estimate is the single value calculated from the sample used to estimate population parameter. And this is difficult to be accurate because, again, it's an estimate, right? The confidence interval is a range of numbers around the point estimate at a certain level of confidence. The level of confidence is the probability that the true value of the population parameter falls within a certain range. And that's where we get this idea of like confidence interval from. So the confidence interval equals the point estimate plus or minus the margin of error. So the lower bound is going to be less than the population parameter, which is less than the upper bound. So that's like a fancy way of saying it's going to fit into that. The population parameter should fit within the lower and the upper bounds. It's a function of the desired confidence level plus the standard error, and the error reflects the inability to capture the true population parameter. So I'm sure you know what you've heard of a hypothesis. We talked about it a little earlier. The hypothesis is, of course, the proposed explanation. The hypothesis test is used to determine if there are statistically significant differences between groups. Is it significant, or is it not random? Is it by chance? It could be two-tailed, different, or is it one-tailed and there's a certain direction of the difference, as you will see shortly. So the steps in testing a hypothesis are as follows. Number one, determine the hypothesis. Number two, set what we call the alpha or statistical significance. I'll explain that a little more in a little bit. Number three, calculate the test statistic. And then number four, reject or fail to reject the null hypothesis using the p-value. So step one, determine the hypothesis. So the null hypothesis, what you see here, h sub 0. So h sub 0 is the base case being tested. We're saying that there's no relationship, not reject or reject. The alternative hypothesis, h sub a, is going to be tested against the null, and that's where we expect there to be we hypothesize there's a relationship, and it's assumed to be true if we're able to reject the null hypothesis. If we have a two-tailed hypothesis, as an example, so if our null says sales on Saturday are the same as sales on Sunday, so obviously there's no difference. And then our research hypothesis, if you will, says sales on Saturday are not the same as sales on Sunday. So that could be, and it's two-tailed because it could be more sales or less sales. The one-tailed hypothesis example, as we see, sales on Saturday are less than or equal to sales on Sunday. That's the null hypothesis. And then the research hypothesis here is that sales on Saturday, notice now it's greater. Above it was just not the same. This one's greater. So that's, of course, one-tailed because we're just going in one direction, i.e. greater. For the significance level, how do we come to the correct conclusion? And this is where I mentioned alpha and that I would talk about it a little more. So think of alpha, the significance level, as typically we as researchers arbitrarily tend to set it to about 0.05. I've seen some, if you want to be very stringent, you could set it to like 0.01. I've seen some go as loose as 0.1, like 10%. So basically, we're looking for a value less than 5% to say, okay, we can reject the null hypothesis, and we believe that our research hypothesis is the case. So how strong does the evidence need to be to reject our null hypothesis and equal to the probability of a type 1 error? So what you're seeing in this table here is exactly that, right? So the null hypothesis is actually true in the population. The alternative is true. And you can see if we reject the null hypothesis when it's true, that's a type 1 error. It's called a false positive. If we fail to reject the null, When it's actually true, that's the type 2 error. Otherwise, we made the correct decision. Now we can use Excel to calculate an appropriate t-test if we desire. It's fairly simple to do this in Excel. You would probably have to have a special pack to do this, and you may not have that on the version of Excel that you use. So all I'll say here is just know that you can use Excel. It isn't a, I wouldn't describe it as a powerful statistical tool, but it is a tool that you can use. And then step 4 is reject or fail to reject the null hypothesis using the p-value. So if the p-value is less than alpha, then we fail to reject the null. The groups are not significantly different. If the p-value is so the top one is p-value is greater than alpha, we fail to reject the null. If the p-value is less than or equal to alpha, then we would reject the null hypothesis. And then we would conclude that the groups are significantly different. So as an example, the alpha is 0.05. As I said, that's pretty much typical in most research studies. The t-stat is 5.16. The p-value is 2.23. So p-value is less than or equal to alpha, reject the null hypothesis. Now, which test is appropriate when comparing two groups? So if they're independent or unrelated groups, we can do what's called a two-sample in Excel. If they're related groups, then each observation in one group can be paired with an observation in another group. And then, for example, like a pre-test versus post-test scores, obviously they're related, right? In Excel, we call that a paired t-test. You may have heard the term correlation. So this measures the linear association or the relationship between two variables by examining how the variables change with respect to each other. So the variable is simply the measurement that changes over time, or you could say varies, or between individuals and subjects. Again, there is a way that you can do that in Excel if you wish to calculate, for example, a correlation coefficient. So the correlation coefficient is 0 if there's no relationship. It's going to be closer to, if it was like 1, it would be a perfect positive relationship. If it was -1, it would be a perfect negative relationship. But we can look at the data here and you just notice it's kind of everywhere. It's not like, it doesn't look like that, it doesn't look like that. So we can indicate that there isn't really any correlation there. As it says, correlation coefficient -1, perfectly negatively correlated. You would never see that, obviously. This does indicate, if you look at it, yeah, it's kind of a downward trend. Obviously, it's not a perfect -1 score, maybe 0.5, maybe 0.6 at the most. And then the correlation coefficient +1, you just heard me talk about that, perfectly positively correlated. So again, you notice here we have a sort of a line diagonally upward to the right. Again, are all these dots on a perfect line? No, but there does appear to be a trend. And then linear regression analysis. This goes back to slope line intercept. Remember, y equals mx plus b. Y is the dependent variable you are predicting. X is the independent variable which help explain the dependent variable. M is the slope of the line. So think about the gradients, right? The steepness and direction. B is the intercept, where the line starts at the y-axis. And it measures the relationship between one output variable y and one or more input variables x. And it's used to predict the dependent variable. So there's a lot of different types of regression. And we don't need to get into all here, but just some of the more common ones. A simple regression, there's just one independent variable. Multiple, probably more common, more than one independent variable. And the line of best fit is the regression model that best expresses the relationship between the data points. As you can see here, so this is an example of a line of best fit. All right, thanks for watching the video, and I will see you all in a future video. Take care.